Good morning. As president of the Ocean Sciences section, it is my pleasure to welcome you to the Sverdrup lecture. I'm not going to go into a long description of the reason that the lecture was named after Harold Sverdrup, other than to say, for people of my generation, we've been around a while, Harold Sverdrup was the principal author of a text, Sverdrup, Johnson, and Fleming, The Oceans, and very much involved in the leadership of Scripps Institution of Oceanography. He made a number of significant contributions as an oceanographer to our field, and for that reason, the Ocean Sciences section, with the approval of AGU, has a Sverdrup lecture to honor colleagues who are following in Sverdrup's footsteps in leadership in our field. It is a distinct pleasure and honor for me to be introducing Professor Rana, who is this year's Sverdrup lecturer. Rana began her career in ocean sciences studying the fundamental chemistry of seawater in conjunction with colleagues at the Rosenstiel School of Marine and Atmospheric Sciences, principally Frank Malero and several others. She then branched out considerably in her purview with respect to oceans and the role of chemicals in the oceans, principally using various chemicals as tracers of oceanic processes. She has devoted herself to these studies in a very distinguished career. In addition, she has served our section and AGU in several capacities, for which we are all very grateful. Rana will be presenting her talk to us today on chlorofluorocarbons, the ocean's inadvertent canary. And looking at the title slide, I'm wondering when the putty tat is going to jump up here.
In a minute.
I'm very pleased, Rana, on behalf of the Ocean Sciences section of AGU, to present to you this certificate to Rana Fine, the 2008 Sverdrup Lecturer for Chlorofluorocarbons, the Ocean's Inadvertent Canary.
Thanks, John. Thank you so much, and thank you all for coming. It's been a long time since anyone remembered my past times in chemistry. I've come quite a distance in terms of my research since then. Let me see how I'm going to do this. I did want to remark a couple of things about Harold Sverdrup, the Norwegian. In particular, his 1947 publication of the Sverdrup dynamics, the relationship between the large-scale circulation and the wind stress curl. That was quite a major contribution. And I also want to talk about the units that he used. 1,000,000 meters cubed per second. 1,000,000 meters cubed per second. That's what we call a Sverdrup. And I'm going to be using that unit today quite a lot. So I hope you'll remember 1,000,000 meters cubed per second. To put it in some perspective, the volume transport of the Gulf Stream is about 30 Sverdrups off the Florida Straits. And by the time it gets up to about 40 north, it's well over 100 Sverdrups. In contrast, all the river water that comes into the ocean, just 1 Sverdrup. So it's quite a difference there, and we'll be talking about various different ranges of Sverdrups. Now I'm going to talk about chlorofluorocarbons, CFCs. They're gases. They're synthetic halogenated methanes. They have the chemical structure for CFC11 that's given here and CFC12 that's given here. And I will mostly be talking about these two CFCs. Their sources are anthropogenic, that is the aerosol spray propellants, refrigerants, and foaming agents. There are an environmental double-edged sword. CFCs are both a greenhouse gas and they are a threat to the ozone layer. And I call them an inadvertent canary because they're bad for our environment, but they've been pretty good to some of us oceanographers and really to a lot of us in terms of learning about the renewal of the oceans. And it's this renewal of the oceans and trends in the renewal of the oceans that we're concerned about today when we think of the role of the oceans in climate. This is a picture of the CFC geeks at a meeting that we had about 8 years ago in Seattle. Some of us some of the geeks who weren't there when Dong Ha Min took the picture. I thank Dong Ha for going through his archives and getting this picture for us. Today I'm going to be showing maps and I'm going to be showing sections of data. And these maps and sections consist of large amounts of data that were the measurements made by various groups. And I'm in most cases not going to thank a specific or acknowledge a specific group when I present the data. So I'm going to take this moment to say thank you to my colleagues here. And some of my new colleagues, including David Ho, the chief scientists on the cruises, Jim Swift's marvelous ocean data facility, for being generous with the data, for being generous with your ideas, and mostly for being just terrific colleagues. Now on to the CFCs. They have we've been measuring them at sea for about 25 years. Using a gas chromatograph. The solubility measurements were made in the laboratory by Mark Warner and Ray Weiss some years ago. Their chemical stability is well known. That is, they're stable in the oceans under oxygenated conditions. Their atmospheric time history is also well known, and it's measured by the AL gauge and A gauge networks that are run out of Scripps. And the atmospheric histories are well known because, of course, their problems, the CFCs, are an environmental problem. This shows the atmospheric time histories of the CFCs, CFC11 and CFC12 on this left-hand axis. The CFC11 is up at about 250 parts per thousand. The CFC12 up at about 545. These CFCs have been increasing in the atmosphere, but you'll note that they have turned over and they've started decreasing, the effect of the Montreal Protocol and the phasing out of the CFCs. It was decided in the last couple of years that because of the phasing out of the CFCs and the turning over of their maximum values in the atmosphere, it would be a good idea to add another tracer to the suite of tracers that we measure on the Clivar CO2 repeat hydrography cruises. And so we've added SF6 to the suite of tracers. It's much lower in the atmosphere. The right-hand vertical axis shows SF6 is about 6 parts per thousand these days in the atmosphere. SF6 is also an anthropogenic gas. It's an electrical insulator in high voltage equipment, and of course it was used very successfully as a deliberate tracer by Jim Ledwell, Andy Watson, and others. And David Ho and Bill Smithy at Lamont have come up with a new compound here for the purposeful release tracer experiments instead of SF6. We use the tracers to get an age, and an age is an elapsed time since the subsurface water mass was last in contact with the atmosphere. We get a partial pressure age, which is made up of the measured concentration in the ocean divided by the solubility correction, and then we can look up the partial pressure on a graph such as this. This can be done for either of the CFCs or for SF6. We get an average age, and the application is usually to upper ocean water processes, and you need to make some assumptions about how much the water mass is in equilibrium with the atmosphere at the time that it leaves the surface of the ocean. The ratio age is another way to get the age from the CFCs. You can see that the CFC 11-12 ratio age has maxed out and is turning back over on itself, and so it's a little more difficult to apply, and we're now starting to use the SF6, CFC 11, or CFC 12 ratio, which is increasing greatly in the atmosphere. And the ratio age is the age of the tracer-bearing component. Now, CFC ages have biases due to mixing. The biases are due to the nonlinearities in the solubility function and the atmospheric source function. Recent work, however, offers us a lot of promise for separating the effects of mixing on the CFC ages and for improving the estimates of, for example, anthropogenic CO2 inventories. We can do this, again, using the pair of CFCs and SF6, and there is a new method that's being used, transit time distributions, in which the idea is that there is no one specific age for a water parcel. Rather, there is a continuous range of time scale for the movement of water from the source to a remote region. And some of the people who've been involved in this are Hall, Hain, Waugh, Quatala, Peacock, Maltrude, Steinfeld, etc. I know I haven't named everybody who's been involved with this. This is a map of the vertically integrated CFC11 inventory in the global oceans through 1994. It's mostly based on the World Ocean Circulation Experiment data. Remembering the basics, CFCs are a gas, so they dissolve most easily in cold waters. And we see the highest values in the vertical column inventory, just equatorward of the North Atlantic Deepwater Formation regions, and then we see the second maximum in the Southern Ocean area that spans the globe here. The area in the Southern Ocean is made up of a lot of waters that we call subantarctic mode waters. They're thick volumes of water that were first discussed in terms of their importance by Mike McCartney. They're gathering up lots of gases, CO2, CFCs, and then spreading these gases into the subtropical gyres of all the southern hemisphere oceans. And I should point out that the anthropogenic inventory map for CO2 looks fairly similar to this. 1% of the atmospheric CFCs have dissolved in the oceans by 1994. This is not a huge amount. However, it's enough to give us some information about the ocean circulation. About 60% of the CFCs had dissolved in the southern hemisphere, and more than 80% in the upper 1,000 meters. This includes areas near the Deepwater Formation. And I'll also point out that the mode waters in this area of the world off South America, we've just, a student working in Miami, Corinne Harton, has done some estimates on the formation rate of these waters using the CFCs, and I'll talk about formation rates in just a moment. Okay, here are some things I'm not going to talk about today. Some of the applications for the CFCs. biogeochemistry, including the work by Gruber and others on the anthropogenic CO2 inventories, oxygen utilization rates, denitrification and nitrogen fixation rates. We've done some work on denitrification. Dennis Hansel has published on nitrogen fixation rates, and Hansel and Carlson are doing some work now using the CFCs to get decay rates for their dissolved organic carbon. Greg Johnson has done some work on the calibration of Argo sensors using the CFCs. What I am going to talk about today are the added dimension of time that the CFCs give. I'm going to talk about circulation pathways, a little bit how they can be used to test models, simulations. I'm concentrating on thermocline ventilation and formation rates. Ventilation, we're defining here today as a water mass in contact with the atmosphere where gas exchange is occurring. And this is, of course, important for our understanding and monitoring of ocean gas uptake and the global CO2 cycle. Also going to be talking about formation rates, and I distinguish between ventilation and formation rates by talking about formation rates being the flux of water into a water mass, leading to an increase in the actual water mass volume. And formation rates are, of course, important for monitoring the meridional overturning circulation. Well, one of the things that's of interest in terms of the ocean's role in climate, we know that when we add the greenhouse gases, we're seeing that there's a stronger hydrological cycle with a high latitude freshening that threatens to weaken the MOC. However, stronger winds, particularly in the southern hemisphere, have strengthened the circulation there. And there are questions as to whether this strengthened circulation is going to be able to counter the greenhouse warming by pumping more gases into the southern hemisphere. I'm not going to answer this question today, but what I am going to tell you about today is I'm going to show that just like for temperature and salinity, the ventilation of the CFCs in the thermocline is linked to decadal atmospheric forcing. For the formation rates, I'm going to show that some North Atlantic deep waters have increased in terms of their formation rate, and that's been compensated for by a decrease in other North Atlantic deep water formation rates. So what we're going to look at today is we're going to look at first some differences in sections. The sections were taken about a decade apart. And one of the things that comes up when you first start looking at data is, well, how representative is a CFC measurement? Do internal and natural and ocean variability affect these measurements, and what are the regions of the ocean that these measurements are most affected? Well, some of the regions are regions of strong CFC gradients. Keith Rogers has been doing some work on the effect of Rossby waves on the representativeness of a discrete measurement. Other areas are regions of high eddy kinetic energy. These maps and similar work, I should mention, has been done by Waugh and Abraham, just published in a GRL paper, in which they use a model to look at similar problems. What I'm showing you today are some model output from Frank Ryan, Cindy Peacock, Matt Maltrude, and their groups at NCAR and Los Alamos Labs. The output is from the Parallel Ocean Program global model, a 1/10 of a degree model, and it has been modified by the model that was originally published by Maltrude and McLean in 2005. The objective here was to assess changes in the CFC concentrations and in the CFC ages that are expected from internal ocean variability. What you see are maps on the 26.5 sigma theta density surface. So this is about 200, 300 meters on the eastern sides of ocean basins, and at least 500 meters on the western sides of ocean basins. The upper maps, which are the global maps, this is CFC concentration and standard deviation from CFC concentration. This is CFC age and standard deviation from CFC age. The models show an ensemble 12-month average for the year 1994, and the standard deviations exclude the annual cycle. So, what you see in reds and browns in the Antarctic circumpolar current, the western boundary currents, the subpolar North Atlantic, that's where we have the largest noise from eddies. And any signal that we're looking for needs to be exceeding this noise level in order to be significant. So we have values as high as 1 picomole per kilogram in the extension of the Gulf Stream and in the Antarctic circumpolar current region. However, for the purposes of what I'm looking at here today, I'm delighted to say that we're looking at things in the center of the subtropical gyres. And there you can see that if we exceed about 0.2 of a picomole per kilogram, we're in pretty good shape in terms of the representativeness of a measurement for 1 year. So, what I'm going to be showing you here in terms of the sections, the figures were prepared and they were gridded and subtracted in Rainer Schlitzer's Ocean Data View program. They were done by Debbie Willey, who works with me. The black contours here are the CFC percent saturation for the 2005-2006 cruise. The green contours are neutral density surfaces. This is the lower thermocline, the main areas that I'll be looking at and highlighting where the mode waters are and the main changes are. You've got a map here of the track, which runs from about 60 south to 60 north. This is 60 south and this is 50 north. Just take a look for a moment at the North Pacific and the whole Pacific, as a matter of fact. This huge area of the ocean, which hasn't seen the light of day in the last couple of decades. No CFCs down there. What we see in the colors that have been superimposed here are that the CFCs have been increasing, and increasing most strongly in the lower and mid thermocline. Huge difference here between the ventilation of the South Pacific and that of the North Pacific. This is again because of the mode waters. If we look at a section that runs across the South Pacific from about 30 south, we can see that the same type of widespread pattern of increasing CFCs, about 20% per decade. Not shown is the South Atlantic, where we see a similar thing that is happening. This shows the Indian Ocean, a section through the eastern Indian Ocean. The difference is about 12, 13 years between the two cruises, and again, the major increase in the lower thermocline. Again, across the whole subtropical gyre, we find in the South Indian Ocean the same type of increases, about 20% per decade. This shows SF6, which was measured recently and successfully by John Bullister and his group. The SF6, much lower concentrations. We're looking at 10 to the minus 15 moles per liter. CFCs are measured at 10 to the minus 12 moles per liter. So these are femtomoles. The high concentrations, nonetheless, are penetrating into the South South Indian Ocean subtropical gyre. And this is a map here of the age of P made from partial pressure of SF6 and the partial pressure of CFC12. In the area of the mode waters, the ages are between 5 and 10 years, and in the intermediate waters, they're about 10 years. So we can use some of that age information to go back to the atmospheric time history and estimate that this increase that we see in the CFCs of about 20% in the saturation is way over what would be expected based on the atmospheric source alone. Now, this shows the top graph, the apparent oxygen utilization, which is just the difference between the oxygen at equilibrium or what it should be at equilibrium subtracted from the actual measured oxygen. You can see that the oxygen utilization has decreased over this more than a decade of the two occupations of this particular section along 32 South in the Indian Ocean. That means that the oxygen has increased over much of the subtropical gyre. This was published in a paper also using tritium-helium data from Bill Jenkins to show that the ages have decreased. In a paper by McDonough et al., in which they show that the increase in thermocline oxygen has reversed what was considered a global trend in the upper ocean oxygen concentrations previously. And in some work that Dean Remick did recently, he showed that all three subtropical gyres, in fact, have increased their circulation and spun up about 20% since the increase in what we call the southern annular mode, an atmospheric index that's indicative of pressure changes in the southern hemisphere. And you can see this increase in the southern annular mode in the last, since in the 1990s, peaking about 1998, and then the decrease thereafter. This increase leads to an increase in the wind stress curl of the subtropical gyres, and it's probably the reason that we see the CFCs on the deeper surfaces have increased as much as 20% over the last decade or so. Now I'm going to look at the North Pacific, and in the North Pacific, the changes are less than they are in the southern in the southern hemisphere oceans. This is a section across 30 north in the Pacific, and we look at CFC percent saturation increases, and they're considerably smaller, mostly on the order of about 10%. The oxygen utilization rate has increased here also, and also in the North Pacific, as with the South Indian Ocean, there's been a reversal of a previous trend in that looking between the time period of 1994 and 2004, there has actually been a decrease in the oxygen utilization, an increase in the actual oxygen concentration in the North Pacific. This is based upon some work that was done by Steve Emerson, Curtis Deutsch, and Sabine Mecking. Mecking's latest paper in 2008 looks at periodic changes along a density surface of about 26.6 sigma theta. The neutral density surfaces are a little shallower than this. And she concludes that the most variability is along this density surface, and it's due to the fact that this density surface is the deepest surface to outcrop in the North Pacific. Some years it may outcrop, some years it may not, and for these reasons it produces large differences and large changes in apparent oxygen utilization. Continuing on to look at the North Pacific, Rolf Sunnerup et al. Just published a paper that came out in JGR Oceans in which they looked at the effect of mixing on CFC ages, and they used some sparse SF6 data that they had in the North Pacific. And just to say in a nutshell what they found was that they found that any increase in the CFC ages could be attributed to mixing, and that really there was no change in ventilation over the period 1991 to 2006 as far as the North Pacific subtropical gyre goes. Okay. Now what I'm going to switch gears and talk about the deeper ocean, and I'm going to talk about the meridional overturning circulation. Of course, it's important for the transport of the climatically important quantities like heat, fresh water, carbon dioxide. There's natural variability in it, and past climate change has been linked to changes in the MOC. And here you see the deep western boundary current. It carries the high latitude source, North Atlantic deep water, into the lower latitudes, down into the South Atlantic, and then into the other oceans, and it's compensated by a return flow of warmer waters. Well, we have a very solid baseline of observations of tritium and helium-3. Got a frog in my throat. Tritium is the radioisotope of hydrogen. We have tritium decaying to helium-3 with a half-life of about 12 years. Tritium entered the oceans in the bomb spike of the mid-1960s, and tritium has, that bomb tritium really swamped anything that was in the oceans from the natural background tritium. Some of the people who've been responsible for measuring tritium, Jenkins and Schlosser on the Clivar CO2 repeat hydrography lines. This shows 2 decades of tritium and helium, the evolution in the subtropics. On the right-hand side of the section is the northern part of the deep western boundary current, and you can see the tritium growing in, growing deeper, growing more equatorward. And then on the left-hand side, you catch the deep western boundary current when it's north of the continent of South America, here at 8 degrees north. The CFC work has built heavily on this early work that Jenkins and Schlosser and Ostland did on the tritium. I want to talk a little bit about what we have learned over the years and what we've confirmed about the meridional overturning circulation from the CFCs. We've identified 2 well-ventilated components, upper North Atlantic deep water and lower North Atlantic deep water. Their pathways, deep recirculation gyres, interior pathways along equatorward flow that was identified by Weiss and colleagues. Going to talk about their timescales, show how you quantify the inventories, and talk about variable rates. Here is a section that consists of the highest CFCs up here against the boundary in the deep western boundary current off the island of Abaco in the Bahamas. Some work that I did over the years with Bob Molinari at AOML. Starts in 1986, the data, and runs to 2004. What you see here is that you have high CFCs elevated in the upper North Atlantic deep water, coincident with what we call upper Labrador seawater, identified as the source region identified by Bob Pickard in the southern Labrador Sea, southern Irminger Sea, and shown recently by Dagmar Kiki to be able to form in the central Labrador Sea. Then we have the lower North Atlantic deep water, Denmark Straits overflow water. We've got the Iceland-Scotland overflow water, which is a minimum in CFCs. So up until about 1994, not much happening at about 2,000 meters. Then suddenly we start seeing high CFCs. That was coincident with properties that we could trace back to the Labrador Sea and to the high North Atlantic Oscillation Index during the time of the mid-80s to the mid-90s. And it gave us a time scale of about 10 years for the transport from the high latitudes, Labrador Sea, to the subtropics. This shows what I call classical Labrador seawater. So we have upper Labrador seawater, and classical Labrador seawater is a little denser below it. Okay. In order to illustrate the deep western boundary current and the interior pathways, these gyres, interior gyres, which are so important for ventilating the interior and slowing down any kind of signal that comes into the high latitudes, I'm going to use this very nice movie that's been made available to me by Frank Bryan, again, Matt Maltrude, Cindy Peacock, and the people that work with them at NCAR and Los Alamos Labs. Again, it's a 10th of a degree simulation, and I've got my fingers crossed that it's going to go. We're going to look from data or the model run, excuse me, not data, from 1950 to 2001. Here we go. It's going to work. Okay. So we see the CFCs coming in about 5 years. They filled up this subpolar gyre. They start heavily filling the Gulf Stream recirculation, and they're down here along the equator in 20 years. They start pulsing out along the equator, and they'll pulse out clearly all the way to Africa. You get, of course, more and more higher and higher concentration values. This is just a really beautiful depiction of the invasion of the transient over this time scale. Let me see if I can run it one more time. Why not? Yeah. Okay. So again, trying to get an idea of the time scales, the maybe 5 or 10 years to fill out this Gulf Stream recirculation, getting to the equator in about 20 years. You see the filling in of these other gyres that are adjacent, deep circulations that are adjacent to the boundaries in the tropics, in the subtropics, and in the tropics. Okay. Now I'll move on from this, and I don't need that. So I can talk about using the CFC inventories to estimate MOC formation rates, reminding you again that a formation rate means we've got an increase in volume. The inventory of a CFC, or SF6, is equal to the integral of the rate, formation rate, times the concentration at the surface, which is a function of time. Concentration at the surface is also a function of the relative saturation relative to the atmosphere, the equilibrium factor, the something to do, factor related to the saturation, and the concentrations in the atmosphere. We're assuming that the rate is constant over a period of the CFC input. If we do that, we can rearrange the equation so that it looks like this, where R, or the rate, is estimated by an iterative calculation where we vary the R until the inventory matches the observed inventory. The method actually works. The CFCs have been entering the oceans in the last few decades. They have not spread significantly beyond the water mass boundaries. Yes, there is diapectinal mixing, but it's a very minor effect compared to the effect of forming one of these water masses. So the deeper the convection, the longer the convection lasts, the larger the inventory is going to be. And the errors are of the order of about 20%. Mainly they're related to assuming that the formation rate is constant over time. I'm going to show you some examples where we can vary the formation rate. This work was first published for the North Atlantic, some work that Bill Smithy and I did, followed up by work from Monica Rine, Dagmar Kiki, and just in a recent paper in Deep Sea Research that we published by LaBelle et al. These are some results. First of all, the figure, the map up here on the right shows the North Atlantic deep water inventory, and yes, for most of the components of North Atlantic deep water, which are listed here, the inventory is mostly still in the subpolar North Atlantic. About 4% has leaked into the South Atlantic Ocean. The upper Labrador seawater, the average value for the period 1970 to about 1997 is about 3 Sverdrups. Classical Labrador seawater a lot larger because it's dominated by that period, the high North Atlantic oscillation, and I'll get back to that in a minute. Iceland, Scotland overflow water, about 5 or 6 Sverdrups. Denmark Straits overflow water, a little more than 2 Sverdrups. Bob Dixon's recent results showing a decade of Denmark Straits overflow water in his mooring data shows an average of 2.5 Sverdrups. And so, I want you to look at this 19.6, 20 Sverdrups that we get, and point out that Bill Johns has some moorings at 26.5 north, which is right about here in the deep western boundary current in 2004. These moorings gave a mean for the meridional overturning circulation of 19 Sverdrups. However, the range was 4 to 35 Sverdrups in 1 year. That's huge. The good news is that the CFCs are going to be available for monitoring the MOC for a long time. Again, they're not yet affected by mixing with other water masses, and the inventory method will be with us for both the CFCs and SF6 and looking at the differences. I want to point out that the first use of this inventory method with the CFCs was done in a paper by Orsi et al., in which they looked at the Southern Ocean rates of formation. They got about 14 Sverdrups for what we call the bottom waters, with another 7 Sverdrups for the circumpolar deep waters, a rate of 21 Sverdrups comparable to that of the North Atlantic MOC. Okay. Continuing on with the Southern Ocean, these sections were made available from Mark Warner. He gave a talk the other day about them. They run from along 140 West, Tasmania over here, and the Antarctic continent here. 3 different occupations, 95, 01, and 07, 08. The minimum in the middle is circumpolar deep water, and all I want to point out here is that up against the Antarctic continent, where the bottom waters, the shelf waters, are entering into the ocean, we see an increase in the CFCs, but it's a piddly increase in the CFCs. It's not a lot. We know that the Antarctic bottom waters have freshened and warmed globally, and we know the properties are changing. Also, we know that the CFC atmospheric sources have leveled off. We're not really sure yet whether this very weak input is indicative of the calculation has not been done as to whether there's a change in the production of Antarctic bottom water. And I'll just point out that Greg Johnson gave a talk the other day looking at the global distribution of the Antarctic bottom waters, their warming, and the changes in the properties. Now I'm going back up where I'm going to stay for the remaining few minutes that I have in the high latitude North Atlantic. This is lower North Atlantic deep water, the Denmark Straits overflow water, and it's some work that was done by Tosta Tanhu, recently published. We see 3 years of data, 1997, 1999, and 2002. These are 4 of the major components to Denmark Straits overflow water. And what I want to point out here is that, for example, in the year 1999, there was a large increase in the component contribution of Arctic intermediate water. And there was a commensurate decrease in the modified Atlantic water that went into the Denmark Straits overflow water. So there's a temporal switching of the components that go into the Denmark Straits overflow water based on the percentage of water masses at the Denmark Straits sill over these few years. This is from a multi-parameter analysis that Tosta Tanhu did, and I need to point out that the components are changing, the properties are changing, but the measurements of transport show they've been relatively constant over the decade. Okay. What hasn't been constant is Labrador seawater formation. Here you see layer thickness. In red, the layer thickness of classical Labrador seawater. In blue, the layer thickness of upper Labrador seawater. This is the North Atlantic Oscillation Index. The huge increase from the mid-80s up into the mid-90s. With that increase, we got an increase in the thickness of the layer of classical Labrador seawater, increase in deep convection, and then after, when the index starts taking a dive, so does the classical Labrador seawater layer. It thins considerably. At the same time, we see that the upper Labrador seawater layer is thinning when the classical is thickening, and we see that it's making a rebound when the North Atlantic deepwater, North Atlantic Oscillation Index decreases. We have the anti-correlation of 0.85, pretty high, between the thickness of the layer of classical Labrador seawater and upper Labrador seawater. This suggests that an increase in the production of one upper Labrador seawater can be compensated for by a decrease in the supply of the classical Labrador seawater. This work was updated recently for me by Dagmar Kiki in Monica Ryan's group at the University of Bremen. Thickness changes mean inventory changes, and that means formation rate variations. And the last slide that I'm going to show you here is some work that Dagmar Kiki again updated. It shows the inventory of upper Labrador seawater and classical Labrador seawater as a function of time. For the first time, they have a beautiful suite of measurements in the subpolar gyre, which allows them to look at changes in formation rates over periods of time. We see that the classical Labrador seawater inventory is 3 times that of upper Labrador seawater back in 1997, after that high in the North Atlantic Oscillation Index. And then we see the inventory of classical Labrador seawater decrease. From this inventory, Kiki et al. Conclude that there was no production of classical Labrador seawater from 1994 to 2003, and there was an increase in the formation of upper Labrador seawater during this time. The changes in stratification that they identify over this period of time suggests that in the future we'll have much more upper Labrador seawater formed, and it's unlikely that there'll be much classical Labrador seawater formed. There are questions of whether these patterns are going to continue or not, and those I'm certainly not going to be able to answer here today. So in conclusion, I'd say that we've been looking at the CFCs with a limited data set for about the last 20, 30 years. Still, the CFCs and the SF6 with this limited data set are very sensitive indicators, highlighting the interior ocean regions where surface-derived anomalies can be transported on timescales of decades. In the upper ocean, as with temperature and as with salinity and oxygen, the CFC changes are linked to decadally variable atmospheric forcing. This is particularly true for the southern hemisphere gyres and for the North Atlantic gyre, which I haven't talked about. Work by Johnson and Gruber has shown that. As a result, in at least the North Pacific and the North Atlantic, the densities at which the water masses are ventilated vary. We probably should consider possible effects of greenhouse warming on the atmospheric cycles, in particular the protracted high in the North Atlantic Oscillation and the southern annular mode, but I haven't considered those effects. These two modes have decreased recently. The tracer data suggests that decreases in the production of classical Labrador seawater were offset by increases in upper Labrador seawater and vice versa. And in contrast, the percentage contribution to Denmark Straits overflow water has changed, but there's no evidence for a long-term trend in the Denmark Straits overflow water transport. The fat lady is still out on the transport or the formation rates of Antarctic bottom water. I think we'll be seeing some calculations on that fairly soon. In the short CFC record, there is no consistent pattern of a global anthropogenic signal of either reduced ventilation or reduced formation rates. So I conclude that the canary is still alive, and I thank you.
We have time for comments and questions. Because the lights are shining rather brightly, if you're in this section here, please wave your hand so that Rana can see you.
Okay.
There's a question.
Yes?
Please come up here. We can't hear you.
No, I'll repeat your question if you want to do it. How successful are the ocean GCMs in simulating the tracer observations? Well, I can be a diplomat or not here. I think that the simulation, for example, that I showed by the N. Carlos Alamos group is a beautiful simulation of the data. Think that the coarser resolution models are having trouble in terms of how deep the gases are reaching into the ocean and which parts of the ocean they're reaching. And I think that the short answer is I think the eddy resolving models are being much more successful. And that shouldn't be surprising. Rick?
You showed very nicely how you can use CFCs to look at the MOC. The question is, what sort of observing system is necessary to continue to monitor this? Because a lot of us believe that this is the key to the whole climate question. And the follow-up is such a system, observing system in place?
Yes, Rick. The question was, Do we have an observing system in place to monitor this important, what we foresee should be changes in the MOC? Do we have a monitoring system that is extensive enough? And that's a difficult question to answer. We have some of the pieces of the monitoring system in place with the moorings downstream from the source region, moorings around the source region. We have some very good repeat stuff going on in the subpolar. We have very scanty repeat stuff going on in most of the global oceans. Very little in the way of deep hydrography, deep tracers, deep CO2 in terms of the most of the ocean basins. We're doing, as you know, a skeletal group of sections there. So the answer is I think we'll barely eke by there.
One more question.
Amy.
So following up on this, it seems like these recent observations from the North Atlantic show that the ocean transport is highly variable and maybe more variable than we thought.
Okay, yes, she just said that. Following up, the ocean transports, the new observations are showing that the oceans are much more highly variable than we thought.
So I had a question sort of a historical perspective. When we started doing this work and we thought the oceans sort of more sluggish, water mass formation rates were sort of constant over time. Do you have to rethink at all the whole tracer business given this highly dynamic ocean?
Do we have to rethink the whole tracer business given this whole dynamic picture that we're given? Think that the beauty of the tracers is that they're integrating over time, okay? So that when you put a mooring out or you go and make a hydrographic section and then you calculate the volume transport across that hydrographic section, it's a snapshot. And if you happen to have been there in November of 2004 when the deep western boundary current was nowhere within 500 kilometers of the boundary, you cannot possibly then say that the North Atlantic deep water has shut down. On the other hand, the tracers are integrating over time and you don't have that highly temporal variability from aliasing in the tracers.
I'm sorry that we need to adhere to our AGU guidelines and be respectful of the session that's going to follow in this room. And so I would ask that if we need to have further discussions, which it seems that we do from some hands that are up, that Rana has agreed that we will go out into the corridor, not up front here, okay, and people will join us out there for a continued discussion. I would ask those who are for the next section, because of the size of the room, please move. I've been asked by the chair that to move into the middle, okay, for that session. And I want to say that clearly the award committee made a wonderful choice for the Sverdrup Award Lecture. And let us join, please join me in thanking Rana for a very nice lecture.
Thank you.